Hi, everybody who's coming into our first lecture of the season. We've got about 67 or so registrants, so we'll just give it a few minutes for everybody to join in, and we'll get going momentarily. In the meanwhile, feel free to unmute yourselves and say hello, or better yet, in the chat, let us know where you're from, and for our own purposes, it's always helpful to know how you heard about tonight's talk, whether it was through our blast email or Facebook, or a friend told you, or however you heard. We're always interested to hear how we're getting out there, how we're getting our name out there. So again, hello to everybody, and feel free to join in the conversation either on chat, or certainly unmute yourselves for a minute and say hello. And then of course we'll mute again once it's time to start the talk tonight.
Yep, I want to say hi to my students and some book group friends, as well as everybody who's a fan of the ASCO.
All right, that's
Hi, Eileen. This is Galen and Helen.
Hey, Galen, good to see you.
We found out because Eileen was courteous enough to send us the information, and we registered from there.
excellent.
This is great.
Yes. Well, there's nothing wrong with shameless self-promotion, that's for sure.
Right.
And it's not even shameless.
Absolutely.
Excellent. Excellent. Well, we have friends from all over the country at this point. So, we're just never sure where folks are tuning in from. A lot of New York, obviously, but, we've had folks tune in from Colorado and California, all over the place. So it's good to see. And our regular audience seems to be back. We haven't done this series in a little bit, but it's not that long. So I'm glad to see some familiar names. Hey, there's Anne. Hello, Anne. Good to see you again, too.
Yeah. And Beryl is an NCPR fan.
Excellent.
It's hard for me to get through a day in the Adirondacks without having somebody ask, "Are you on the radio?"
Yeah. Kevin LaPlante from Tupper Lake. We should have had a watch party right here at my house. That would have been fun.
That would work.
All right, we'll just give it another minute or so. I'll do a brief welcome, tell you about just a couple of things that are happening, and then as should be, I'll let Eileen loose on the Sagittarius A star. Again, if you've just joined us, please feel free in the chat to let us know where you're joining us from and how you heard about us. It helps us with our with grant writing in a lot of cases, because our grantees like to know how far our reach is. So it's important. The wider our spread, the more I don't know. I guess the more important they think we are. But it's nice to have a varied crowd. And this is the first. Well, I guess I'll wait until we actually start to. It's the teacher in me. I want to take attendance, but I have to wait till wait till the bell rings to do that. All right. Well, I'm going to say that we'll start, and we'll get going so that we can get to everything tonight. Good evening and welcome. My name is Seth McGowan. I'm the president of the Adirondack Sky Center and Observatory. We're a not-for-profit organization rooted in making astronomy accessible to everybody. In a lot of cases, at least I know from my perspective, growing up, I thought that astronomy was for the astrophysicist and those, really big, smart people, and it certainly is. But that does not mean that the average person can't enjoy astronomy at whatever level they want to. So that's sort of our mission. That's kind of one of the things that we want to really bring out to folks, is that we are, about astronomy for everybody. So with that, I want to just tell you about a couple of events that are coming up. One very important one, if you haven't already heard, the astrophotography conference was on a 2-year hiatus because of COVID. We are back this year. Registration is open right now, and I'll put a link in our chat in just a little while to tell you about, to show you where to register for that. And just by means of explanation, that is a conference whereby no matter what level of astrophotography you're in, you can always gain some more experience by being with others. And if you look at the little picture on the right side of the screen there, it shows our roll off. And this is a drone picture of some folks getting set up for the astrophotography conference. And the reason that this exists is because when you're doing astrophotography, it's at night, it's dark, and oftentimes it's in the winter, so it's cold. And if you're having a problem, trying to look up the solution on your phone on YouTube is extremely, dangerous. Frostbite sets in pretty quickly. So this is really set up to have astrophotography experts come and stand with you hand over hand and help you solve the problems that you have when you're doing astrophotography. We have our sessions that are that we do our imaging in the evening. And then over on the left-hand side, you can see we have a classroom where we do the processing of those images. And that is, again, hand over hand. You're very well supervised. You can work at your own level. But when you run into a problem and you don't know why your images are not coming out the way you think they should, there's somebody there with a ton of experience that have seen the problems that can help you out. So it's a very guided and collaborative kind of an event. And there's a lot of camaraderie. All of the groups that have come over the years still stay in touch with the folks that they met there. And I know some of them are on this call, tonight, so they can certainly attest for that. So anyway, registration is open now. It's $300. It's a 4-day event, and there's nothing else like it. Nothing else like it that at least I'm aware of. So if you're into astrophotography or even thinking about it, give us a call. The other event I wanted to make sure you knew of is that we have arranged for a total solar eclipse to come to Tupper Lake for your enjoyment pleasure. The Adirondack Sky Center and Observatory is bringing this event to you live on April 8th in 2024. And I want to say that if you are an eclipse chaser and you've been to eclipse events like a total solar eclipse, Tupper Lake is in the center of totality, and you know what that feels like. That's a very exciting, a life-changing event, I will say. So book a room now. And the word is from some of the hotels both in Tupper Lake and in Saranac Lake in the region, that rooms are starting to fill up for April 8th, 2024, and the days prior to it. The Adirondack Sky Center and Observatory will have a number of activities all around the eclipse, not only that day, but we'll be doing outreach to schools in the area. We'll be having eclipse ambassadors going out to the communities and doing some stuff with the community. So again, April 8th, 2024. I'd like to say that, you can't see it anywhere else. I'll say that, but you'll know that I'm kidding. But the best place to see it, I can say, will be in Tupper Lake. We are the only place in the region that's in totality that has the kind of observatory and people here to help enjoy that experience. So, and we're collaborating not only with the county, but the local town and village of Tupper Lake are all on board. So we're really looking forward to that. All right. Now, before we get started for the night, I just want to remind you, if I didn't mention it already, two things actually. One, of course, that our presentation tonight will be recorded or is being recorded. So it will appear on our YouTube channel sometime over the weekend. So you can look for that. If you haven't signed up or visited or liked our YouTube channel, all of our talks are on that from the very beginning. So if you're scrolling through and you want to see something from 2 years ago, it's in there and you can enjoy that at your leisure. The other thing I wanted to mention is you may see at the bottom of your screen that we have a live transcript now coming along on the bottom of your screen. And that was a special request from some folks that had some hearing deficit. And so we've enabled this feature within our Zoom environment so that you can read along some, hopefully it'll get some of the terminology if that comes up. This is the first time we're trying it, so we hope that it helps. So enjoy that as well. Now, without any further ado, we have back with us again for, I would say, the 100th time, Dr. Aileen O'Donoghue, professor at St. Lawrence, professor at St. Lawrence University, and is a board member of the Adirondack Sky Center and Observatory. If you haven't seen her before, it's likely that you've heard her before on North Country Public Radio when she tells you about things that are coming up in the night sky. Her enthusiasm for astronomy and every related subject is contagious, and I always look forward to her talks. So tonight is the Sagittarius A-star supermassive black hole in the center of our very own Milky Way Galaxy. So Aileen, take it away.
All right, thank you very much. All right, so let me share screen. I'm going to take it away from you.
All right, great.
And there you can see my PowerPoint. Let me go ahead and start it. So you can all see this okay?
Yep.
I hope.
Yes.
And so, okay. Yes, this supermassive black hole in the center of our own galaxy. They have been working on this. You may have seen that the Event Horizons Telescope, they did release the image of the black hole in M87 a few years ago. This one they observed, did some of the observing at the very same time, but it's been a more challenging image for them to finally create. So that's why it was only released this year. So the sky, so what I'm going to go through here is the sky tonight. And so you can see where you can point at Sagittarius A-star. We can't show it to you because it's blocked by gas and dust, but we can point at it and you can look at the Event Horizon Telescope and some other images that I'll show you. And then I'll kind of go out and get perspective a little bit on galaxies in the Milky Way and the center of the Milky Way. And then this amazing telescope, Event Horizon Telescope, and then black hole images, because black holes are black. They don't emit light. How can we make an image of a black hole? And so what we're making an image of is the light emitted by accretion disks. That light is created a lot by synchrotron radiation. And then I'll compare a little bit Sagittarius A-star and the black hole in M87. And then the last slide will just be that astronomy is amazing, and it's getting more and more amazing. I hope some of you were able to watch the live feed from NASA when they released the first 5 images from the James Webb Space Telescope. And those were snapshots. I mean, those weren't deep images where they looked at it for a long time. So There's just amazing stuff happening all the time. And astronomy is accelerating in the excitement. So the sky tonight from the roll-off roof observatory at 11:30 p.m., you'll have this nice moon. I guess it's into the waning gibbous here. And notice you can see the swath. I assume you can see my mouse okay? So this swath, of course, is the Milky Way. That's our galaxy. And so among all these stars, these colors are a little more defined than they look when you're outside. But among these stars, here's a bright red one. And that is one of my guideposts on the night sky. That's the bright star Antares. It's very red. And Antares means the rival of Aries, the rival of Mars, because it is so red. And Antares is in Scorpius, the scorpion. And so the scorpion is this lovely long constellation, ends in these two stars very close together called the Stinger. In New Mexico, where I studied for my PhD, it was called Los Ojos de la Virgen, because she, as my pastor would say, she is watching you. Okay, you can't get away with anything. And so then the other important part, it's Sagittarius A star. So Sagittarius must be here. And maybe you can see there's a little teapot shape here. I'm a little no, I won't do that. And so that is, it's not the constellation, it's called an asterism. It's a recognized pattern that's not one of the official 88 constellations that are designated by the International Astronomical Union. So that is the teapot. And of course, it has a companion teaspoon. And those are part of Sagittarius. But the teapot is pretty easy to spot if you can see Antares and the Stinger. The teapot's easy. Now it's big at arm's length. It's bigger than your hand. So these are large on the sky. So there are a couple of constellations. Here are some stars in Sagittarius: Nunki, Acela, Caus Australis. Caus Australis is the southern part of the arrow because Sagittarius is the archer, not actually a teapot. And so this is Sagittarius's arrow, and Sagittarius is aiming at the heart of the scorpion, because the scorpion is running around the sky trying to bite Orion for ancient reasons. So that's Scorpius, Sagittarius. Oh, that's the zodiac. What sign comes after Sagittarius? Anybody got an idea? Did I hear it? Capricornus. And so the mergoat, right? You've heard of mermaids. Well, Capricornus is a mergoat. And so here are some stars in there: Algete, Davy, and Deneb Algete. This is the tail of the goat. This is the goat. And notice the moon is sitting right in Capricornus tonight. I don't see a mergoat in this. I see an upside down communicator from Star Trek. So that's what I point out. And when I look for it in the sky, I look for these two stars and these two stars. And oh, wait a minute, look at this. What's this guy? That's that's not supposed to be there. So maybe it's one of these pesky wandering stars. And yeah, there are those. And yes, that is Saturn. So Saturn is still in the constellation of Capricornus, which means it is in the direction of the constellation of Capricornus. The constellations form a political map of the sky. That is, each constellation defines an area. And so Saturn in Capricornus means it's in the area of the constellation of Capricorn. And so, all right, so if you didn't get the other quiz about the zodiac, so Scorpius, Sagittarius, Capricornus, what comes before Scorpius? Anybody know? It's after Virgo, and then it's Libra. And the thing about Libra is those stars have the coolest names in the sky. They have names like Zubin el Janubi and Zubin es Shamali. Oh, these should be N's. Sorry, I have a misspelling on it. Zuben with an N. And Zuben es Shamali means the northern claw, and Zuben el Janubi means the southern claw, because these used to be the claws of the scorpion. So that's why they have such cool names. And so remember to change that first M to an N. And so that's our zodiac. And then looking around, here's a couple of stars right along the Milky Way that are interesting. And these are Altair and Tarazed, and they are part of Aquila the Eagle that is winging its way along the Milky Way, northward along the Milky Way. Cygnus the Swan is winging southward along the Milky Way. But I have a hard time picking an eagle out of that, so I just think of it as the manta ray. And look, it's even got this little stinger down here. So it's the manta ray of Aquila. And then we got another pair of stars over here. Those are Russell Hugway and Russell Gethy. And Russell Gethy is in Hercules, which is off the top of this chart. Russell Hugway is in a constellation that the astrology people don't tell you about, which is Ophiuchus. If you were born in late November, early December, you probably were born under the constellation of Ophiuchus, and they don't even put your horoscope in the paper because it's so magical. So if you were born in that time, first couple of weeks of December, look, talk to an astronomer. We can let you know if you're an Ophiuchian. But Ophiuchus is actually holding a snake. He's the snake bearer. He may be, as well as the biblical story about the snakes on the poles to looking at the snake on the pole would cure a snake bite. Well, Ophiuchus is the snake bearer and a healer. And so he is holding a snake. And so here's Serpens Capu, the head of the snake, and Serpens Cauda, the tail of the snake. So it's a very busy place, this part of the sky. And then over here, we just have a couple little shapes that are fun, a couple of tiny constellations, Delphinus and Aquilus. Aquilus is the horse, Delphinus the dolphin. So those are the stars in this region. And on Friday night, Seth and Gordy and Mark and their laser pointers can show you where all of these are. So let's put some of our coordinates, though, our other things on this image. And so here, this is actually the ecliptic. This is the path of the sun. It goes along the zodiac because the sun crawls through the zodiac. That's why you have a sun sign when an Ophiuchus butts in down here so that the ecliptic actually passes through Ophiuchus now. And so that, yes, notice Saturn is very close to that. Saturn, the moon isn't very far from it either. All of the planets, this is the plane of the solar system. It's actually the plane of Earth's orbit. So the others are off by a little bit because all of the orbits tilt slightly. The moon's is 5 degrees off of Earth's orbit. So that's that. And then there's another line. Well, here, an important point for us, this is the winter solstice. So when the sun is there, this little nebula, little bright spot there is the Lagoon Nebula. And you can look at it with the telescopes. Can you see that far? You can see that from the RoRo, right?
Oh, absolutely.
And so,
Absolutely.
yeah, you can look at the Lagoon Nebula. It's a lovely star-forming nebula. It's wonderful. And it gives you a good marker for where the winter solstice is. So when the sun is there, most people like it when the sun is past that and moving toward the spring equinox. So then this arcing over this part, this is the celestial equator. And this is the line, if the Earth had rings, we would see the edges of the rings going along this line. And the stars move parallel to this because as Earth rotates, all right, our point of view is moving parallel to that equator, and we move at 15 degrees per hour. And so you'll see that all the stars move relative to that. And then the last line I want to put on here is the galactic equator. So that is the equator of our galaxy. And here is the meridian of the galaxy. And so what that means is that right in here is the center of our galaxy. ding, Sagittarius A, Sagittarius A star is the very center of our galaxy. So that's where it is. You can kind of make something up from the teapot. You know, the spout doesn't quite point at it, but it's close enough. You know, make a, you know, it's make something up and point in that direction. You're fine. You know, you can be wrong, just don't be in doubt. So galaxies, these are systems of billions to trillions of stars. The Milky Way Galaxy is our home galaxy. Here's a photograph of it over my beloved land of enchantment, New Mexico. And it has, you hear different estimates, but somewhere around 300 billion stars. And it's a barred spiral. So my students are always very glad to hear that, yes, the Milky Way does have a bar. And so when they're of age, they can go there. But this is what it looks like. So let's zoom in on this and look at where we live. And so here's this nice image of the galaxy. And making this was, you know, a feat in itself. This has taken generations of work. But here is the long bar. Here's a galactic bar. And right here, the coordinates, of course, are centered on us because we made the map. And so here is the sun right there. And it's on the inner edge of the Orion Spur of the Sagittarius or the Perseus Arm. Now, Seth and I are looking at this and we can't decide if we're attached to the Sagittarius Arm or the Perseus Arm, so make it up. But that's where we sit in the midst of this. And near one of the spiral arms, oh, I'm very sorry. And I clicked on the picture and brought up the web page. So let's zoom in a little closer, and here you can see, yeah, maybe we're connected there. Maybe we're connected over here. It's really hard to say, but that's where we live. And so Sagittarius A star is in the center of the galaxy. So the center of the Milky Way. Sagittarius A, astronomers are very clever. The brightest radio object in a constellation is named A. So Sagittarius A is the brightest radio object in Sagittarius. And it's about 27,000 light years from the sun and Earth. 1 light year, just to remind you, is the distance light travels in a year. And it's moving at 186,000 miles per second. Oh, that's wrong too. I'm going to make some corrections on this. That was incorrect. It should be 186,000 miles per second. And so 1 light year is about 6 trillion miles. It's a fair piece. And so Sagittarius A star is actually behind a couple other spiral arms. So we can see, you know, here's the Centaurus arm, the Norma arm. And so it's blocked from our point of view by the dust and gas. It is visible in radio, all right? Cell phones come through the clouds, they don't see clouds. And it's visible in infrared. The heat comes through the smoke. And so we can see it in these different wavelengths of light. And we have different telescopes that pick up on these different wavelengths of, it's all really light, and it's an electromagnetic fluctuation. But the different wavelengths, different frequencies have to be detected in different ways. And so Sagittarius A star is then the brightest radio spot in Sagittarius A. And it has been, when I was a graduate student, one of my graduate colleagues, who's now a professor in I can't remember where he is, but he was making some of the preliminary radio images of Sagittarius A star. So it's been looked at, you know, for 35 going on 40 years.
Wow.
So this caught our attention because the stars orbit the center of this thing, Sagittarius A star, at very high speeds. We've been observing these stars. People have been observing them mostly in infrared since 1995. And so here is an image. This is the near infrared. So this is the heat coming through the smoke, basically. And Sagittarius A star is in here. It's not really very impressive there. It gets impressive by the motions, not its appearance. And so here, This is 1995.5, so June of 1995. I'm going to click on this. This is a video. This is where Sagittarius A star is. And you're going to see these stars. These are individual stars. And they are going to orbit this, and it will trace their paths. And this is amazing. Watch the years go by. So there we go. 1997, 99, 2001, 2003, 2005, 7, 9, 10, 11, 12. Look at this. Years, half a career of work here to 2020. All right, 25 years of watching that. And so as you watch these again, look at how they speed up when they come close. So, doomp, and this guy, doomp. They really speed up. And Isaac Newton told us, if we know the speed of something in orbit, we can calculate the mass of it, what it is orbiting. This is old clunky physics that you all had in high school. And so these motions tell us the masses of these stars. And so I'll tell you what we conclude from those. The other thing we've seen from Sagittarius A star is increased X-ray flares, the number of them. All of a sudden, there's a bunch of flares since 2014. We have a bunch of X-ray satellites, and at least 3 of them have been observing Sagittarius A star since 1995. So they've been monitoring for a long time, and yeah, it'd flare now and then in X-rays. But then in 2014, they started getting an increased number of them. And there was this cloud of this thing, G2. It's an object they had identified, and it was orbiting. It didn't look like a star, and they thought it was a cloud of gas. And they could see that it was going to go have a very close passage by this black hole. And they expected to get ripped apart. Well, it didn't. And we didn't get an immediate flare from it. And so, well, now they're going back at their desk trying to figure out what G2 is. And these flares have continued. So there is one idea that material from this object, whatever it is falling in more slowly due to interactions with material going around the black hole. So here is Sagittarius A star, and here is G2 going by it. And then here, some of this stuff is getting sucked into the black hole. And on these, by the way, I put the URLs on these slides. So if you want to go see where I got this, you can do this. So yeah, they don't really know what G2 is, but this is an artist concept of what might be going on here. So the Earth Horizon Telescope, to look at the black hole in the center, we need a big telescope. And so Earth Horizon Telescope is the size of the Earth. The radio observations of different telescopes, and now we have the Greenland telescope up here. We observe all at the same time by atomic clocks. And then we have to bring the data together and analyze it as though these are different patches of the same telescope, which takes a huge amount of computing power. So here's a newer image. All right, GLT, SMA, LMT. What the heck are all of these things? And here are the images. All right, well, they're names. So here's the sub-millimeter telescope, and I've got this thing that I can't, oh, sorry. Trying to get rid of this zoom thing and can't figure out how to do it. But you can, these are hidden by Zoom for me, but the Greenland telescope, Institut de Radioastronomie Millimétrique in France. All right, we have one in Texaco, in Mexico. All right, the Large Millimeter Telescope. We have the South Pole Telescope. These telescopes all over the Earth, some in the Atacama Desert of Chile, So all these telescopes, they observe the same part of the sky, the same position at the same time. And then what the process is, so here are the different telescopes, different antennas, really. And they convert from an analog signal. You know, what you get in radio astronomy, what you actually detect is a changing voltage. That's what we actually detect in radio. Just like you had the radio with the dipole antenna, there were, an electric field came by and it jiggled the electrons up and down. That's what happens in a radio telescope in its most simple form. And so that's an analog signal. It's jiggling electrons. You get a voltage that's some kind of a wave, can convert that to digital and make sure you correlate it with the atomic clocks, because it's very important that these be at the exact same microsecond, millisecond, nanosecond. And then write it onto hard drives. They can't put this information over the internet because it's too much information. And so they have to actually write all the data to hard drives, and then they take the hard drives on commercial airliners and fly them. And they fly some to MIT and they fly some to Max Planck, and they do independent analysis. They don't work together to come up with the answer. They work independently and look at a variety of ways to what configuration of material and emission would create the radio waves that they receive. And it's, any of you who do math, it's Fourier transforms, and they work on different scenarios from different models to figure out which model gives them the waves that they see. The way to bring it back to the Adirondacks is to think about, if you're lying on the dock and you're looking between the slats and somebody lobs a big rock out way out in the pond, you see waves that come past you. They look like a plane if that rock is far enough away. If they throw a handful of gravel, then you get these kind of rumply waves where you've got, one rock's wave on top of another rock's wave. And so what they do essentially in this data reduction and analysis is they have this crumply wave that hit the Earth and detected by these 8 telescopes. And they have to use math to reconstruct what was the distribution of pebbles thrown into the pond to create this. And there are, different answers. There are different ways to do this. And so they focus on getting the best one. And that takes years of analysis, which is why these images have been so slow to be released. So what are we looking at? You can't see a black hole. No light gets out of it, and it absorbs all the light from behind it, around it. So what do we see? Well, we do see it absorbing some of the light from behind it, so there is a shadow. But also, there's a disk of material falling into this black hole. And that is glowing because this stuff is hot. And because it's moving very fast, it's charged particles, they're accelerating, so they emit light. And so the black hole, what it does is it warps that light into a ring, warps the image of the disk into a ring, and it requires a lot of observation time and intense computing, as I was saying, creating an image from 8 pieces of a telescope laid out on the Earth, very widely separated. And they have to do all these calculations on how the black hole is going to bend the light from what's around it. So a big player in this is the accretion disk. And that is material here. As stuff falls in, there's always one plane or another that's more crowded. Stuff can fall in from the top and it just goes right in. But you develop a plane like the Galaxy has a plane where it's more crowded and stuff is trying to spiral into the black hole. And so that material is going to accrete onto the black hole. That's why it's called an accretion disk. And this is very hot. And so particles are flying off in all directions. But these are charged particles, so they create a magnetic field that is shown here by this twisted tube. And that twisted tube constrains the particles to stay within it. And so we have bipolar flows in two poles coming out of these black holes in places like M87. We don't see it from Sagittarius A star, but this is part of what black holes do. So here's just a larger image of that showing the magnetic field lines. We get the jets, and here's the accretion disk. So the way that charged particles emit in radio is that you saw we had a lot of magnetic field lines around there. The black hole itself has a magnetic field embedded. And when particles, a charged particle comes by a magnetic field line, if it's coming in, it doesn't just cross it, it spirals around it. And so as it's spiraling, it's being accelerated toward the magnetic field line, just like when you go around a curve, you're actually being accelerated toward the center. Your coffee cup that is not being accelerated by the body of the car then flies to the outside of your car. And so these charged particles caught in these magnetic fields, mostly electrons, as they zip along here, they emit in the direction they're moving. And so we see things the brightest when the particles, the charged particles, are moving at us. And so here is our image of Sagittarius A star. It's fuzzier than M87, and I'll show you that one in a minute. But we can say about this bright part, that's probably where charged particles are coming at us. And that's why it is brighter. So after the release of the M87 image, NASA created this very informative diagram of an idealized image of a black hole. The black hole is in here. And so the black hole's shadow, where it's blocking all the light that's coming in from behind it or any other direction. And then you see this ring. And that ring is actually where light came so close to the black hole, it didn't fall in, but it went into orbit around the black hole. And so we can, some of that can, just outside of that, we can see some of that light that does actually get out. So that hasn't fallen into the black hole. It's just going around it. And then these different parts of the image. So this over the top, that's actually the far side of the disk, and the light is going up from there. I guess I got to do it this way. Light is going up and bending around into our eyeballs. And so that's coming at us from the far side of the black hole. Underneath here, this bottom one, that's from the bottom of the disk, and it's getting bent around the black hole and coming at us out the side. And then here is the actual accretion disk, where the material is actually, where we're seeing the material. And here it shows the Doppler beaming. This is where the Doppler beaming is that the particles shine brightest in the direction of approach. So this is the brightest part. That's where the particles on the accretion disk are coming at us on that side, and they're going away on the right side. So this disk, we're looking down from above, is rotating counterclockwise. So here is that in motion. And again, this is from the NASA webpage. Just Google NASA black hole diagram, and you'll be able to find these and read the explanations. And yeah, it's a dynamic system. So these, lanes, it's particles are running into each other, and that's why it's so dynamic there. So the center of our Milky Way, we got Sagittarius A star. We saw the stars orbit at high speed. And so the mass, so here's an image, the image of it. And the mass that has those stars orbiting is 4.3 million times the mass of the sun. And the diameter of this event horizon, way in here, is 16 million miles. the radius or the distance from the Earth to the sun is 93 million miles. So this isn't the event horizon. Mercury's orbit is outside of, way outside the event horizon. But that scale, 72 million miles, 27,000 light years away, that's 8 billionths of a degree. That's how big this is. That's why they needed a telescope the size of the Earth. Because we're looking, as this, the last line says, we're basically looking at a donut on the surface of the moon from the Earth. That's so exciting that we can actually figure out how to do that. And if you hold your pinky at arm's length, your pinky should span about a degree. So 8 billionths of the width of your pinky held at arm's length. That's how big this is on the sky. Just stunning that we can look at this image. So the black hole is 4.3 million times the sun mass and a volume of 0. Yeah, only God can divide by 0, and the universe divides by 0. So let's look at this image I have for my background here. And this is where I snitched it, okay? So this is from an ALMA. This is the ALMA, the Atacama Large Millimeter Array. And that's mostly run by the National Radio Astronomy Observatory in Charlottesville, Virginia. A friend of mine worked for them for a long time. And but it's an international effort, as are most telescopes now. They're just too expensive for one country. And so there are those telescopes, and the people at the Earth Horizon Telescope. Here's that image. That's where Sagittarius A is, right there. A pinpoint above these antennas. Wow, wow. So we saw the M87, and it's much less fuzzy. Notice that this is Pluto's orbit. This is Mercury's orbit. All right, so Pluto's orbit is about 100 times Mercury's, all right, much bigger. This is how far Voyager 1 has gotten. So this is well outside the solar system. This is huge. M87 is utterly huge. Sagittarius A star, it's much smaller than Mercury's orbit. So it's a tiny, tiny black hole, and it was a much harder image to make. So M87, the mass is about 1,000 times the mass of Sagittarius A star. The distance is about 1,000 times greater, and so they're about the same size. Well, their size is scale as their distance. So M87 also is a billionth of your finger held at arm's length in the sky. But there are other reasons that the Sagittarius A star is just a fuzzier image. The observations that we have to make of these take hours, if not days. And for M87, for this material to orbit M87, it took a few days. But for Sagittarius A star, we have a helicopter going over. For Sagittarius A star, it takes a couple of minutes. So Sagittarius A star is blurry because the motions, we just can't overcome those motions. We have to observe them for a long time to collect enough light to be able to get any information. So the image of Sagittarius A star is blurrier than M87 due to the motions. And it was also harder to create due to these motions. They change a lot of things in the light that we're getting. Also, Sagittarius A star and Earth, we're sitting in a very dusty galaxy. And we're both in about the plane of the galaxy. There's a lot of gunk between us and Sagittarius A star. M87 is not in a spiral galaxy, it's an elliptical galaxy, but we can see right in. We don't have to look through a plane full of gas and dust. So it was a clearer view of M87. And so that's one of the reasons that was easier to create than Sagittarius A star.
Hmm.
So one of the other things is, why the hell is it orange? It's not orange. We make it orange. And we make it orange because we can see more levels. And they've studied this, and orange is easier for us to see. Here's just a white and black, a grayscale. You can't see nearly the detail as you can here, because here it not only goes from bright to dark, but it goes from yellow to red. And so we can express a wider dynamic range if we use orange. And so orange is becoming the standard for images in low frequencies. But you saw in the images released by James Webb Telescope on Monday that we also do look at colors in different frequencies, and we'll assign red, green, and blue to different frequencies, although we wouldn't see it that way because it's all infrared. We would detect it as heat, but they can assign colors. So that's what false color is that we've assigned colors to frequencies that our eyeballs would not see in that color. And so that's why the image is orange. And why blobs? Here's Sagittarius A star, and there are these blobs. Here's M87. It's a little less blobby. Part of that is the motions. Part of that is, we've got gunk blocking some of the views of Sagittarius A star. But the Doppler beaming, some of them are blobs. They're just blobs in these accretion disks. But some of it is Doppler beaming. The blobs are going to move. The Doppler beaming position is going to stay in about the same spot because that's just the motion of the disk. And so for Sagittarius A star, we think this is the Doppler beaming region. And then for M87, this is the Doppler beaming region. And so remember, when you're looking over the top, this is the accretion disk on the other side of the black hole. This is the underside of the accretion disk on the other side of the black hole. So it's hard to really get a perspective. So up, 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 up. So that's about it, what I have for the black holes. But astronomy is so amazing. This is an incredible week for astronomy. It's the Earth Horizons Telescope has just released the second image of a black hole. We're going to see more. They're doing more work. We're going to see more detail. The images are going to get better as we learn how to put this information together. And they have two independent teams working independently so that we can be more confident of our answers. And they're going to be learning more. And then this is the James Webb Space Telescope Deep Field that they released just 2 days ago, 3 days ago.
Tuesday.
And
yeah.
it's a cluster of galaxies. And look at this. Every one of these is a galaxy. Here is the Hubble Space Telescope image of that. And remember how amazing Hubble has been. And here it's just red blurs. Now, looking at how red that image is, you can probably see why James Webb operates in the infrared, because it's getting too red for us to see invisible. So we need to look in the near infrared with James Webb. And the spiky things in this image, these are the stars. Anything with no spike is a galaxy. So look at these. And in the announcement, they picked out some tiny little red blur and looked at the image and were able to talk about this galaxy that we're seeing over 13 billion years in the past. We're seeing it when the universe was only a few 100 million years old. I mean, the Himalayas are older than some of these galaxies when we're seeing them. And then these warps here, those are images of more distant galaxies, because this is a cluster of galaxies. There's a whole bunch of galaxies here. And yet beyond it is another cluster of galaxies. And the light from those galaxies comes by these galaxies, and gravity bends light. That's what we just saw with the black holes, is that the light from the far side of the accretion disk comes over the top, gets bent into our eyeballs by gravity. This is the light of a distant galaxy being bent by the intervening galaxies. So we can study these galaxies far beyond what we could see if this cluster of galaxies wasn't changing and magnifying these images. So it's just awesome what is going on. And every day there's just more exciting news with astronomy. So yeah, there's that. And the adventure continues. So that's my spiel.
That is mind bending. Forget about the light. That is just mind bending.
Yes, yes, yes.
Let's open up for some questions and
Yeah,
discussion.
just pop on and ask or comment, whatever.
Unmute yourself. Be mindful of others that might be trying to unmute as well. But let's go for it. Actually, my first question, Eileen, is those hard drives that they're bringing by airplane. There's backups and duplicates of those, right?
Oh, absolutely. Some on site. Yeah, yeah. Multiple travelers carrying them. Some of them are left on site,
Excellent. Good to hear.
Yeah, hard drives fail, but nothing else can carry that amount of data.
It's funny because I always grew up thinking a black hole was a sphere. It was like just a very dense, planet or, object that was just crushed down and just massive but spherical. And what I'm
Well, and they
understanding,
are pretty much spherical. I mean,
Okay.
they're, oblate spheroids or prolate spheroids or something because of rotation. But what we're seeing is not the black hole. What we're seeing is the light bending around the black hole due to this very dynamic accretion disk.
right? Okay.
So that's why it doesn't look spherical.
And are we able to see the jet of materials that is going through the magnetic pole there?
With in M87, we are able to see it. Not in the image of the black hole, but certainly in X-ray and other images. We have very good images of that jet.
Okay.
And the jet has been known for a century. People saw it early on with the first Palomar images. They could see that jet. And I think it was actually identified by eye by somebody before they even had images. I can't remember
Wow.
quite. But
Okay, that's cool.
yeah.
All right, I've reached my quota of questions. Somebody else
Right. Any
unmute.
questions, comments? There's only one stupid question, and it's, is this going to be on the exam? And the answer is no. I interrupted someone.
Hi, Eileen and Seth. This is Ann. I had
Hi, Ann.
I had a question for you on the computational side. So
Yeah.
you said they sent it to MIT and to Max Planck, but I don't recall that was the two areas that the first black hole was defined from. Were they? I thought it was in
I thought that those were two of the centers of analyses. There may be other centers of analysis too, but
Okay.
yeah, I think Max Planck certainly.
So do
And
they have to
and I
agree
thought
on
MIT.
something? Do they
Huh?
have to agree? Do they have to agree on certain things, or are they really independently looking at independent observations?
They're looking at the same observations, and they're using models. They're modeling and seeing what their models predict for this image to appear as. And so they do use independent methods, and because if they're getting at what is true, then no matter which approach you use, you count on your fingers or your toes or an abacus or a calculator, you should get the same answer, right? And so they don't even talk, I don't think, until they come up with some of their preliminary images, and then they'll start saying, okay, what are you guys getting? This is what we seem to be getting. And then they challenge each other and really try to get at what is the best understanding. So,
Thank you.
Great question.
by the way, a lot of very young people are involved in this because they are the ones, computational astrophysics is a field now. I have a young woman who just left yesterday from St. Lawrence. She's headed off to the University of Illinois for graduate school in computational astrophysics. And that's where they do all this computer modeling of things like these black holes. So there's all kinds of stuff going on, and young people are making a huge contribution to astronomy as amateur astronomers do, you know.
Mhm.
There's too much to learn. We can't just do it the professionals.
Well, there's a little bit of a lull. I just want to point out that in the chat, I've put all of our contact information from our YouTube channel to Facebook, email, website, phone number, and so forth. In addition to the link to register for the astrophotography conference in September. And if you hadn't heard, we are building a planetarium right here in Tupper Lake on our site with our observatory. That will be a nice pairing of, meal and wine, so to speak. It'll observatory and planetarium paired together. So we are beginning fundraising for that. If you are interested in that, please contact our office, certainly, or me directly, and I'll put my email address in the chat. But please don't be shy about making a donation or passing that information along to somebody who you know who might be interested in contributing to the construction of a planetarium right here in the crossroads of the Adirondacks in Tupper Lake. And now back to our program.
Yeah, and I put my email if any of you want to come up. I'm very bad at coming up with questions at the time of a talk. So, you can just copy that and shoot me an email, and I'm happy to answer any questions. I can, make the PowerPoint available once I make the corrections. You work on the damn thing and you're too close to it. You can't see these
That's-
obvious errors.
That's true.
No.
All right, any other questions out there? I put a question out on our Facebook page a few days ago, and I don't know if it was too intimidating for people to think about or just not ready to think about, but it was, how do you think the James Webb Space Telescope will change our perspective? And I intentionally left it ambiguous. Some people ask me, perspective on what? And I refuse to say on what. I want to know what your thoughts are on how those images and that information will change our perspectives. So if anybody has any thoughts on that now, or want to visit our Facebook page and take a stab at answering that question. It certainly is an exciting time in astronomy. You can just feel it. I mean, you can just feel it. How many, how many stories on the news are astronomy related? How many commercials are you seeing now with kids with their pretend helmets on, eating cereal in the morning, imagining themselves on a rocket ship? We haven't seen that in years.
Yeah.
So there is definitely this unbelievable surge in interest in astronomy. And I think that these talks move us in that direction. I think the Adirondack Sky Center and Observatory is definitely moving us in that direction, but you can't help but notice it anymore. Astronomy is the thing these days, and including astrotourism. People are traveling to dark sky sites, just like Tupper Lake, especially when, we can bring you something like a total solar eclipse. That's even better reason to come.
It is so hard to break into the sun's schedule. Oh,
I know that's why we had to do it 2 years in advance. Their booking agent was really upset about that, but
yeah.
we got
So-
him. We got him.
Yeah, for your question, Seth, I think that if it's true to the pattern, what James Webb is going to show us that the universe is even weirder than we can imagine. And and it's just going to blow our minds.
Well, it certainly has tonight, as
Well,
you always do.
It occurred to me that what is it, 5 or 6% of the observable universe is all we really have access to. And then there's all this unknown, this dark energy and dark
Dark
matter.
matter and dark energy, yeah. Normal
So I think
stuff
that
is
the
about-
James Webb will help us in that regard to find out a little bit more about the nature of reality.
Oh, that's good.
Yep.
The nature of reality, astronomy, philosophy and astronomy. That, you know, that kind of a course might be something that we see more and more in the future.
Yeah, well, you know, physics in the old days was called natural philosophy,
Hmm,
Cambridge and Oxford.
no, okay, did not know that. That's great. All right, well, Eileen, thanks for not just bending light, but bending our minds tonight. As always, you know, your talks are so engaging and just so enlightening and
I need a bigger
education.
screen. I can't fit myself.
Well, you are talking about the universe, so, you know,
Yeah, that's true.
I don't know if they make
So,
one.
well, thank you everyone for coming. I hope you enjoyed it. Feel free to shoot me an email if you have a question. And it's nice to see all your names there. Not too many cameras on, but thank you all for coming. It's
Yes.
always fun.
All right, thanks again, and thanks everybody, and we'll see you online. Again, look for this posted over the weekend if you want to pass it along to some of your astronomy friends or non-astronomy friends for that matter. All right, good night, everybody.
Ciao.
Bye-bye.
Right.